Welcome to Next Gen Manufacturing. Today, we are diving deep into a fascinating, kind of invisible science. It's the science that keeps our most advanced tech from, well, falling apart. We're going to look at the secret life and the slow death of the materials that literally build our modern world. I mean, just think about that for a second. How on earth do you guarantee that a brand new jet, built from all these amazing, revolutionary, lightweight materials, can handle the insane stress of flying, not just for a year, but for 30 years? The answer is all about predicting the future. All right, let's get into it. So here's our game plan for today. We'll start with the incredible promise of these next-gen materials. Then we'll uncover the invisible threat that's always trying to undermine them. After that, we'll see how scientists basically forecast their future, and then we'll climb what's called the pyramid of confidence. And finally, we'll see how this all makes next-gen manufacturing not just possible, but safe. Okay, first up, the next-gen material promise. You know, we're living in the middle of a lightweight revolution, and it's all being driven by this one remarkable class of materials. We are talking about polymer composites. And engineers, they absolutely love these things for a few really good reasons. One, they slash weight, which is huge for saving fuel. Two, they let you combine a bunch of different parts into one single piece, which makes manufacturing so much simpler. And three, they can actually bring costs down. It's no wonder you find them everywhere, from airplanes and cars to massive ships. Now, here's something that might surprise you. When you hear the word composite, you probably picture that sleek, high-tech black carbon fiber, right? But take a look at the data. By sheer volume, it's actually humble glass fiber that makes up a whopping 90% of the market for reinforcements. Carbon fiber, it's just 1%. Kind of wild. And what's holding all those fibers together? Well, that's the job of a polymer matrix. And in this arena, thermoset resins, like the epoxies you might have heard of, are the undisputed champion. They make up 70% of the market. They're super strong, really stable, but as we're about to find out, they are not invincible. And that leads us to the puzzle at the heart of all of this. For all their high-tech advantages, these incredible materials have this slow, creeping, totally invisible enemy. It's the one thing that can undo all of their amazing promise: aging. So let's go on the hunt for this invisible threat. Let's play detective and identify exactly what causes these amazing materials to slowly break down over time. You see, aging isn't just one single thing. It really falls into two main camps. First, you've got physical aging. This is where the material's basic chemistry stays the same, but its physical structure changes. Think about a sponge absorbing water. It gets heavier and swells up, but it's still a sponge, right? Then you have chemical aging. This is where the material itself is chemically attacked and actually transformed into something new, kind of like a piece of iron rusting. So what's causing all this? Well, it's a whole gang of environmental aggressors. Heat and humidity are probably the two biggest culprits, but you've also got sunlight, just the constant stress of being used, exposure to different chemicals, and in some cases, even tiny microorganisms looking for a snack. And the worst part is, they often work together, ganging up on the material to speed up the damage. And this quote right here, this absolutely nails it. It tells us where the attack is most effective. See, it's not always the fiber itself that fails, or the resin. So often, it's that microscopic boundary between them, the interface. That's the weakest link in the chain. It's where moisture and stress can get in and start to pry the material apart from the inside out. Okay, so if these materials degrade so slowly over decades, how in the world can we design with them today? Well, that brings us to our next section, forecasting the future of materials. It turns out scientists have basically built a time machine to solve this exact problem. And this time machine is called accelerated aging. The whole idea is pretty simple, really. You obviously can't wait 30 years to see if a material is going to hold up. So instead, you put a sample of it in a special chamber and you crank everything up, the heat, the humidity, the UV light, to create this super aggressive environment that mimics decades of wear and tear in just a few weeks or months. But, and this is a huge but, there's one critical rule. You have to speed up time without changing the story. The damage you create in the lab has to be caused by the exact same things that would happen naturally out in the real world. If you just end up cooking the material and causing some weird artificial damage, well, then your prediction is totally useless.
Which, of course, leads to the all-important million-dollar question. How do we know we can actually trust these predictions? How do we know this scientific time machine is showing us the real future and not just some science fiction fantasy? Well, the answer is a super rigorous four-phase methodology. First, you get to know the brand new material inside and out. You characterize everything about it. Second, you push it to its limits to define its breaking points. Third, you run all those accelerated tests on small samples, modeling exactly how they degrade. And fourth, this is the crucial last step, you validate. You compare your predictions against real-world data from older materials to prove your model actually works. This whole structured approach is easiest to understand if you picture it as a pyramid. So let's talk about the pyramid of confidence. It's a great way to see how engineers build up their proof of safety, starting from the tiniest scale and working all the way up to the full structure. So at the very bottom, the wide, strong base of the pyramid, you start with these small, simple little squares of the material called coupons. This is where you test the absolute basics. How hard can you pull on it before it snaps? How much can you crush it? This gives you all that fundamental data you need to build on. Okay, moving up a level, you get to elementary specimens. Now, these aren't just flat squares anymore. They might be simple joints or maybe pieces with holes drilled in them. The goal here is to start seeing how the material behaves around basic structural features you'd find in a real part. At the third level, things start getting way more complex. Now you're testing large structural elements. I mean, things that actually look like a piece of an airplane wing or a section of a car's frame. At this stage, fatigue testing is king. You're simulating thousands and thousands of hours of real-world stress. And finally, we get to the very peak of the pyramid, the sub-assemblies. This is pretty much the last step before you can certify the whole thing. You take a massive section, like an entire wing box, and you test the heck out of it to validate that every single prediction you made at those lower levels holds true when it's all put together. So, what does all of this get us to? Well, it brings us to our conclusion: manufacturing the future safely. All of this deep, incredibly detailed science is what unlocks our ability to innovate and build amazing things with confidence. And this isn't just about airplanes. This ability to predict and manage how materials age is fundamental to next-gen manufacturing across the board. We're talking space exploration, high-performance cars, ships, high-speed trains, even massive bridges. It is the hidden science that ensures everything is safe and built to last. Which really leaves us with this final thought. Today, the big challenge is understanding that slow march of heat and humidity on our composites. But as we start manufacturing with even smarter materials, self-healing materials, adaptive materials, maybe even living materials, what new invisible threats will we have to conquer next? Thanks for joining me.